Hi, this video is a presentation for Physics 2211 Lab 5 on the motion of a falling slinky. In this video, I'll introduce the experiment and explain some key terms and formulas, show my analysis of the physically observed motion, produce a complementing computational model, compare the results between these two processes, and conclude by discussing the ramifications of this experiment. The first key concept to understand is Newton's second law of motion. This law tells us that the net force of an object is equal to its mass times its acceleration. The momentum principle, which states that the change in momentum is equal to the net force times the change in time, is also very useful. It is also important to have some basic understanding of the types of forces present in this experiment. First, the force of gravity is caused by the pull of the Earth's mass on the slinky. Tension is a type of contact force when a wire, in this case the slinky itself, is pulled by forces acting from opposite sides. Drag is a force generated by the interaction and contact of the slinky with the air around it as it falls. Additionally, a few key formulas to be familiar with are the velocity update and position update formulas. These two formulas, along with the formula for average velocity, help us determine the final velocity or position of an object at any given moment. The formulas for calculating the force of gravity and the force of drag are also included. To observe the condition of the slinky in this experiment, I imported the given video into Tracker, calibrated the program, and tracked a specific point of mass on the end of the slinky as it moved throughout the duration of the video. The program took each of these data points and generated a position versus time graph, which can be seen on the right side of the screen. With observational data now recorded and analyzed, I moved to the second portion of the experiment, which was to create a computational model based on my experiment. Using GlowScript and available code as a template, I was able to generate expected results for the conditions of my observational data. These real-life conditions needed to be reflected in the code, and therefore some aspects needed to be changed. First, under the initial conditions section, I updated the mass of the slinky and the vector for the initial position of the ball to reflect the video analyzed in Tracker. I also added the value of 9.8 for the value of g, gravity, in this experiment, and found the value for b, representing drag due to air resistance, which was 90. In the calculation loop, I needed to demonstrate two distinguishable parts to this experiment: how the bottom of the slinky moved before and after contact with the rest of the slinky. First, I changed the parameter while t is less than blank to be the same value as the final time point from the Tracker data, which was 5.733 seconds. Then I incorporated key formulas so that the net force of the slinky could be properly calculated. A similar process was followed on the second section of the calculation loop, but the time interval changed and the formulas were slightly modified to more accurately reflect the effects of drag on the slinky as it traveled in this part of the experiment. Using the data from both the observed and computational models analyzed, a graph can be generated to compare the two of them, and the results overall are very positive. The computational model appears to reflect the real-life conditions with a high degree of accuracy and precision. And each model was able to prove that the bottom of the slinky didn't move significantly until the rest of the slinky had already fallen. Reflecting on this experiment, we can better understand what happened during the experiment and how the bottom of the slinky appears not to move. We can see that the bottom of the slinky initially remains stationary because the tension force of the slinky, which essentially is a large spring, is equal to the force of gravity. This means that the bottom of the slinky is in a static equilibrium because the two forces acting on it are opposite and equal. One major what-if question that comes to mind is what would have happened if the top of the slinky wasn't dropped from rest, but instead, if an additional downward force had been applied to the top of the slinky when it was released. For example, if the person holding the slinky, instead of just dropping it, had pushed the slinky down instead of just releasing it from rest. We would expect to observe a modified version, obviously, of the motion to compensate for this additional force, but all the same principles previously discussed would still apply. The tension of the slinky would still be an important factor, as well as the gravity. This experiment also is a fantastic way for us to gain a greater understanding of the forces involved in this system, which was our fallen slinky, which exhibited characteristics of motion that I didn't initially expect. When I first thought about this experiment, I didn't expect the bottom of the slinky to stay stationary during that first section, so it was cool to be able to see the differences there. And allows me to better comprehend the momentum principle, which is a key concept for this class. And understanding the underlying physics of this experiment helps us understand even more about the world around us. Thank you.